Okay, now we're going to the next level. So up to this point, we've compared at most two groups, right? Or group 1 to group 2. Or one score to a population or something along those lines. What ANOVA does, ANOVA stands for analysis of variance. What it does is it allows you to compare more than two groups on some independent variable or on some dependent variable. So for example, using this last analysis, right? It would be easy to, the analyses we've seen so far, it'd be easy to compare, say, men and women, right? But how would you compare different ethnic groups? You could do a whole bunch of them, right? But you couldn't sort of do them all at once. That's what ANOVA allows us to do. By the way, hopefully this isn't confusing at all, but it should be stated that while this comes up as sort of a new topic, and it is a different thing because it allows us to do more stuff, ANOVAs and t-tests are actually the same thing. If you ran an ANOVA with only two groups, you get what's called an F value. If you took, the F is t squared, yes. If you took the square root of that F value, it would be the exact same as if you ran the equivalent t-test as the t value. The reason for that is because you'll notice that these t-tests were using difference between means, and they're using the standard deviation, right? So you're asking how many standard deviations are these things off from each other? But you remember the standard deviation is the square root of variance? You guys remember that from the earlier slide? ANOVA works directly off of variance. So think of it this way. Z-tests, t-tests, z-scores work off of standard deviations. ANOVAs work off of variance, right? Variance is standard deviation squared, F is t squared. Of course, you can't get t values for comparing more than two groups. But in that special case where you were running an ANOVA and you could have run a t-test, it's the same exact thing. You're not doing anything different. The math will look different, but it's the same once you get under the hood. So in a one-way ANOVA, you're using one categorical independent variable with more than two levels. Notice that I brought back the measurement here. The reason I say it's categorical is because you can't do this if you have, say, an interval independent variable. That's not true. You can do it with an interval independent variable, but you have to break it into categories. Because you're asking about different groups, right? So you can't have a group that's on a scale. It's not like one group can fade into another group. You're asking about discrete groups. Are these three groups different from each other? If I give you Prozac versus not give you Prozac versus give you coffee, right? Those are discrete categories. If you were to do this with a continuous variable, how much Prozac do I give you and how well do you feel? You can either break that into groups and run ANOVA, or you can do it in regression, which we're going to come to. But it's just important to realize that your independent variables here are categorical, and your dependent variables are the ones you want to be interval. And if you think about it, that's actually the case for all the t-test and z-test stuff we just did, right? I didn't explicitly say it because we were just talking about two groups. But here we're talking about multiple groups, but it's an independent variable, right? So before it was like group membership was the independent variable, but now you can think of the independent variable as, say, state that you live in. You could compare 50 groups, right? Does that make sense? Okay. You can do stuff with interval ratio independent variables, but generally you want to do that in regression. And then to do this, you want the categorical independent variable with more than two levels and an interval level dependent variable. This is why, remember I said it's really important how you measure these things. You can't run ANOVA if you've got nominal data. I guess you could if it was ordinal. I wouldn't do it. You want interval level data. I think you can get around some of these other things and if you really know what you're doing. I don't know enough to do it. I think there are some kinds of workarounds you can do, but I wouldn't mess with it if you don't know well what you're doing. So this tests what's called the omnibus null hypothesis. Right? So before we were comparing, is group 1 the same as group 2? Now we're asking, is group 1 the same as group 2, the same as group 3, the same as group 4, same as group 5? And all that it tests, the ANOVA itself, all that it tests is whether or not they're all the same or whether or not they're not all the same. And now you may notice, well, I didn't care about whether 2 and 3 were different. I just want to know if 1 was different from 2 and 3, right? I just want to know if 1 stuck out from the group. In order to test those specific hypotheses, rather than just, oh, they're all different, but to say like, oh, 1's actually different than 2, you do what are called post hoc tests or what are called contrasts. I don't have time to get into it. There's whole literature on these things, but this allows you to ask more specific questions like, is mean 1 greater than mean 2, right? rather than just are they all the same or not. And there, again, there's a whole bunch of stuff to go along with this, so I can't really get too much into it. But just be aware that the way that you do that is with contrast and post hoc tests. Post hoc tests are basically, they're generally just independent samples t-tests for all the different comparisons, and they do some correction for the fact they're doing a whole bunch of them. Okay, so one way AnoVa, basically the logic of how this works is like this. In the same way that I've been talking about estimating what's going on in the population, let's say you've got 3 samples, right? And you want to know, do they all come from this one population or not? How would you estimate the variance of that population? How much would you expect scores to vary from the population? Similar to how we did the independent samples t-tests, we want to use the variance from within all of our groups, right? If all of these 3 groups kind of look the same, they all have similar spread, they all have similar dispersion, similar distributions, we should take all that information somehow and say that's probably what the population looks like, right? In other words, if you think of the population as just one group, they all vary for all of these reasons, these random reasons. I woke up late today, you didn't have coffee this morning, you're feeling great, whatever. There's always sort of random variations, right? I grew up West Coast, you grew up East, it doesn't really matter. But that's random variance because it's not systematically connected to anything that we're concerned with. If you want to know if Prozac works, and I'm happier today because my mom is visiting, right? That's irrelevant to the question of whether or not Prozac works, right? It's random. And it's random because it only applies to me and has nothing to do with what we're talking about. Whereas for you, it might be that you grew up in, California, and that's totally different. Or it could be, that you've had a rough day, and that's totally different. So it's random variance, so it's how things are varying just randomly due to sort of chance circumstances, right? And the amount of variance you see within these samples is a pretty good estimate of how much in general that happens, right? Because these samples, you're assuming they're all the same. One of them I gave Prozac, one of them I didn't, one of them I gave coffee. The amount that they're all varying naturally within themselves is a pretty good estimate for how much the population should be varying naturally within itself, right? Does that make sense? So the way you say that is that this within group variance of these samples gives you an estimate of the random variance of your population. Does that make sense? Here we go, next step. The between group variance, so the difference between the means. The placebo group is at 1, the coffee group is at 3, and the Prozac group is at 10. That 1, 3, 10 difference in means, you can use that to then calculate between group variance, right? There's some tricky math that has to be done to get a good estimate of this. And I'm going to come back to that here in a minute. I'm going to set that aside for now and just mention the reason why you're going to see between group variance is both random, right? If you have one population and you take 3 samples out of that population, just randomly, the means are going to be a little bit different, right? You might get 1, 2, and 0.5, right? Just randomly. So it's both that random variance that's there, but it's also the systematic variance of, I gave them Prozac, I gave them coffee, and I didn't give them anything, right? So the systematic variance means it's tracking your variable, and the random variance means it's just these noise factors. My mom's in town, you're having a bad day, you're, sick or whatever. Does that make sense? So within group variance, within these samples, gives you an estimate of the random variance from the population. The between group variance tells you both the systematic variance between your samples as well as the random variance in the population. Does that make sense?
The systematic?
Systematic. And systematic just means it's sort of all going in one direction, right? So random variance, like in physics, you would talk about random variance as just, if we all just jumped up and just started running around in circles, that would be random variance. But if we jumped up and started running in circles and there was a strong wind going that way, we'd all sort of slowly be moving that way. So you'd have both the random variance of us just running around, but you'd have the systematic variance of us sort of slightly going this way eventually. That's a rough description of the mathematical formalism, I guess. Okay, so all that an AnoVa does is it compares these two. And I'm going to go through 3 different ways, 3 different ways of thinking about this comparison. There's a whole bunch of different ways to conceptualize what an AnoVa is doing. Hopefully just one of them will stick. If they all stick, awesome. They're all completely equivalent to each other. It's just different framings, okay? So What this does is it compares the variance between the different groups to the variance within the groups. Boom, that's our F ratio right there. You get an F statistic rather than a T statistic or a Z statistic. You look it up in an F table rather than a T table or a Z table, but it's the same basic idea, right? Does that make sense? So I'm going to give you a couple extra ways to think about this. Hopefully these are helpful. Pulling from information theory, you can think about this as signal and noise, right? So in the example I just gave, if we all jumped up, right? I give everyone coffee and we all jump up and we freak out and we're just running around in circles. That's just noise, right? It's just random variance. Think of it as white noise on your TV, right? But then if a strong breeze started coming, I mean like real strong wind, we'd all sort of start moving that way, pretend that wall's not there. That's the systematic variance, that's our signal, right? That's the signal of the wind. Another way of thinking about it is that if you're looking at a whole set of information, right? Within that information, there's going to be a bunch of noise that you don't care about. Things are just randomly going to be kind of all over the place, but there might also be a signal, right? In that noise, and this compares the ratio of the signal plus the noise to just the noise itself. Let me try and push this one step further and say this is what happens when you tune your radio. You know when you're in between stations and it goes shh, that's noise, and when you hit the radio station, what's happening is there's a capacitor in there that pulls the signal out of the noise. That noise is still there. In fact, all the radio stations are always still there. Wherever you are, all it's doing is amplifying that signal to drown out the noise.
Why don't we just cancel out the noise and just like...
signal over noise plus one? Yeah.
Oh, you mean mathematically? Like
no,
why can't I
if
just
you
do it?
imagine it's like what we're doing is just measuring the ratio of the signal basically to the noise. Like, I feel like, I don't know, I never understand why we can't just to a certain degree cancel it out.
That's more or less kind of what you're trying to do. If you think about it, there's no possible way you could ever measure the pure signal without also measuring noise. There's no way I mean, that's not totally true, but in general, especially in social science, there's no way you can just get the signal. What's the effect of Prozac? Well, I don't know. I can just give it to people and see what happens. So there's always going to be noise there. And so you are, in essence, trying to do that.
But you just inevitably have to factor it in.
You're trying to take your signal plus noise, the only thing you can measure, and then get an estimate of your noise so you can sort of cancel it out and say, oh, that part's accounted for, and we've got something way beyond that.
Okay.
That is, in essence, what you're doing, actually. That's a good way of putting it. Is that another? Again, I told you there's like 4 different ways you can think about this. All right, here comes the next one. Are you guys ready? It also compares expected to observed, right? Noise is the expected amount of variance that we're going to see by chance, right? Signal plus noise is the amount that we actually observe. If those observations are about the same, your F ratio is about 1. By the way, no result corresponds to an F ratio of 1. So if you think about what that would mean in these 2 equations here, that would mean observed is exactly what we'd expect just from noise, right? If you think about the one up above, if there's 0 signal, you would just have noise over noise, it would also equal 1. F ratios of 1 are basically nothing's going on. Takes an F ratio of about 4 to get statistical significance. Okay, does this make sense?
So would
Yes.
the noise be like if you have like a control group, would the noise be just a control group, like you would say like you observe something without actually simulating?
Sure. Yeah, let's say we're a control group and I give the next class Prozac, right? And you ask us how happy we all are right now, I guarantee we're not all going to be equally happy. You guys are listening to this boring lecture, maybe some of you guys like it more, some of you guys like it less. There's going to be variance within us, but it's not systematic, it's just randomly, right? So if we measured them before we gave them Prozac, they would also be noisy. And then we give them Prozac, you can imagine measuring us is to get an estimate of what that noise is.
Basically that's all we do when we get it involved.
Yeah, roughly, when you're doing these. It's one way to think about it. Another way is, you could think about us as, what's the expected variance? And then look at them and say, okay, what's the observed sort of variance between us? And are those the same, or is the observed actually much greater than we would have expected to see by chance? If it is a lot greater than we'd expect to see by chance, then we say it's unlikely that they're the same, and therefore we provide support for our research hypothesis.